Desalination.
Desalination, desalinization, and desalinisation refer to any of several processes that remove some amount of salt and other minerals from saline water. More generally, desalination may also refer to the removal of salts and minerals, as in soil desalination. Salt water is desalinated to produce fresh water suitable for human consumption or irrigation. One potential byproduct of desalination is salt. Desalination is used on many sea-going ships and submarines. Most of the modern interest in desalination is focused on developing cost-effective ways of providing fresh water for human use. Along with recycled wastewater, this is one of the few rainfall-independent water sources. Due to relatively high energy consumption, the cost of desalinating seawater are generally higher than the alternatives, fresh water from rivers or groundwater, water recycling and water conservation, but alternatives are not always available. Desalination is particularly relevant to dry countries such as Australia, which traditionally have relied on collecting rainfall behind dams to provide their drinking water supplies. According to the International Desalination Association, in June 2011, 15,988 desalination plants operated worldwide, producing 66.5 million cubic meters per day, providing water for 300 million people. Production is expected to reach 120 million m3 by 2020. Some 40 million m3 is planned for the Middle East. The world's largest desalination plant is the Jebel Ali Desalination Plant, Phase 2, in the United Arab Emirates. The largest percent of desalinated water used in any country is in Israel, which produces 50% of its domestic water use from seawater desalination.
Methods.
The traditional process used in these operations is vacuum distillation, essentially the boiling of water at less than atmospheric pressure and thus a much lower temperature than normal. This is because the boiling of a liquid occurs when the vapor pressure equals the ambient pressure and vapor pressure increases with temperature. Thus, because of the reduced temperature, low-temperature waste heat from electrical power generation or industrial processes can be used. The principal competing processes use membranes to desalinate, principally applying reverse osmosis technology. Membrane processes use semi-permeable membranes and pressure to separate salts from water. Reverse osmosis plant membrane systems typically use less energy than thermal distillation, which has led to a reduction in overall desalination costs over the past decade. Desalination remains energy-intensive, however, and future costs will continue to depend on the price of both energy and desalination technology.
Considerations and criticism. Energy consumption.
Energy consumption of seawater desalination can be as low as 3 kWh per meter 3, including pre-filtering and ancillaries, similar to the energy consumption of existing freshwater supplies transported over large distances, but much higher than local freshwater supplies which use 0.2 kWh per meter 3 or less. The laws of physics determine a minimum energy consumption for seawater desalination around 1 kWh per meter 3, excluding pre-filtering and intake outfall pumping. Under 2 kWh per meter 3 has been achieved with existing reverse osmosis membrane technology, leaving limited scope for further energy reductions. Supplying all domestic water by seawater desalination would increase U.S. domestic energy consumption by around 10%, about the amount of energy used by domestic refrigerators. Energy consumption of seawater desalination methods. Note: electrical equivalent of thermal energy is the electrical energy that cannot be produced in a turbine because of extraction of the heating steam.
Cogeneration.
Cogeneration is the process of using excess heat from electricity generation for another task, in this case the production of potable water from seawater or brackish groundwater in an integrated, or dual-purpose, facility where a power plant provides the energy for desalination. Alternatively, the facility's energy production may be dedicated to the production of potable water, a standalone facility, or excess energy may be produced and incorporated into the energy grid, a true cogeneration facility. Cogeneration takes various forms, and theoretically any form of energy production could be used. However, the majority of current and planned cogeneration desalination plants use either fossil fuels or nuclear power as their source of energy. Most plants are located in the Middle East or North Africa, which use their petroleum resources to offset limited water resources. The advantage of dual-purpose facilities is they can be more efficient in energy consumption, thus making desalination a more viable option for drinking water. In a December 26, 2007, opinion column in the Atlanta Journal-Constitution, Nolan Hertel, a professor of nuclear and radiological engineering at Georgia Tech, wrote, "Nuclear reactors can be used to produce large amounts of potable water. The process is already in use in a number of places around the world, from India to Japan and Russia. 8 nuclear reactors coupled to desalination plants are operating in Japan alone. Nuclear desalination plants could be a source of large amounts of potable water transported by pipelines hundreds of miles inland." Additionally, the current trend in dual-purpose facilities is hybrid configurations, in which the permeate from a reverse osmosis desalination component is mixed with distillate from thermal desalination. Basically, 2 or more desalination processes are combined along with power production. Such facilities have already been implemented in Saudi Arabia at Jeddah and Yanbu. A typical aircraft carrier in the U.S. military uses nuclear power to desalinate 400,000 U.S. gallons, 1,500,000 L. 330,000 imp-gal, of water per day.
Economics.
Costs of desalinating seawater, infrastructure, energy and maintenance, are generally higher than the alternatives, fresh water from rivers or groundwater, water recycling and water conservation, but alternatives are not always available. Achievable costs in 2013 range from $0.045 to $1 per cubic meter, $2 to $4 per gal. The cost of untreated fresh water in the developing world can reach $5 per cubic meter. Average water consumption and cost of supply by seawater desalination, plus/minus 50%. Factors that determine the costs for desalination include capacity and type of facility, location, feed water, labor, energy, financing, and concentrate disposal. Desalination stills now control pressure, temperature and brine concentrations to optimize efficiency. Nuclear-powered desalination might be economical on a large scale. While noting costs are falling, and generally positive about the technology for affluent areas in proximity to oceans, a 2004 study argued, desalinated water may be a solution for some water-stress regions, but not for places that are poor, deep in the interior of a continent, or at high elevation. Unfortunately, that includes some of the places with biggest water problems. And, indeed, one needs to lift the water by 2,000 meters, 6,600 feet, or transport it over more than 1,600 kilometers, 990 miles, to get transport costs equal to the desalination costs. Thus, it may be more economical to transport fresh water from somewhere else than to desalinate it. In places far from the sea, like New Delhi, or in high places, like Mexico City, high transport costs would add to the high desalination costs. Desalinated water is also expensive in places that are both somewhat far from the sea and somewhat high, such as Riyadh and Harar. In many places, the dominant cost is desalination, not transport. The process would therefore be relatively less expensive in places like Beijing, Bangkok, Zaragoza, Phoenix, and, of course, coastal cities like Tripoli. After being desalinated at Jubail, Saudi Arabia, water is pumped 200 miles, 320 kilometers, inland through a pipeline to the capital city of Riyadh. For coastal cities, desalination is increasingly viewed as an untapped and unlimited water source. In Israel as of 2005, desalinating water costs 53 cents per cubic meter, 0.053 c/per liter. As of 2006, Singapore was desalinating water for 49 cents per cubic meter. the city of Perth began operating a reverse osmosis seawater desalination plant in 2006, and the Western Australian government announced a second plant will be built to serve the city's needs. A desalination plant is now operating in Australia's largest city, Sydney, and the Invagi desalination plant was under construction in Invagi, Victoria. The Perth desalination plant is powered partially by renewable energy from the Emu Downs wind farm. A wind farm at Bungendore in New South Wales was purpose-built to generate enough renewable energy to offset the Sydney plant's energy use, mitigating concerns about harmful greenhouse gas emissions, a common argument used against seawater desalination. In December 2007, the South Australian government announced it would build a seawater desalination plant for the city of Adelaide, Australia, located at Port Stanvac. The desalination plant was to be funded by raising water rates to achieve full cost recovery. An online, unscientific poll showed nearly 60% of votes cast were in favour of raising water rates to pay for desalination. A January 17, 2008, article in the Wall Street Journal stated, in November, Connecticut-based Poseidon Resources Corporation won a key regulatory approval to build the $300 million water desalination plant in Carlsbad, north of San Diego. The facility would produce 50 million U.S. gallons, 190 million L. 42 million imp gal, of drinking water per day, enough to supply about 100,000 homes. Improved technology has cut the cost of desalination in half in the past decade, making it more competitive. Poseidon plans to sell the water for about $950 per acre-foot. That compares with an average $700 an acre-foot that local agencies now pay for water. In June 2012, new estimates were released that showed the cost to the Water Authority had risen to $2,329 per acre-foot. Each $1,000 per acre-foot works out to $3.06 for 1,000 gallons, or 81 cents per cubic meter. While this regulatory hurdle was met, Poseidon Resources is not able to break ground until the final approval of a mitigation project for the damage done to marine life through the intake pipe is received, as required by California law. Poseidon Resources has made progress in Carlsbad, despite an unsuccessful attempt to complete construction of Tampa Bay Diesel, a desalination plant in Tampa Bay, FL, in 2001. The board of directors of Tampa Bay Water was forced to buy Tampa Bay Diesel from Poseidon Resources in 2001 to prevent a third failure of the project. Tampa Bay Water faced 5 years of engineering problems and operation at 20% capacity to protect marine life, so stuck to reverse osmosis filters prior to fully using this facility in 2007. In 2008, a San Leandro, California company, Energy Recovery Incorporated, was desalinating water for 46 cents per cubic meter. While desalinating 1,000 U.S. gallons, 3,800 L. 830 imp gal, of water can cost as much as $3, the same amount of bottled water costs $7,945.
Environmental intake.
In the United States, due to a 2011 court ruling under the Clean Water Act, ocean water intakes are no longer viable without reducing mortality of the life in the ocean, the plankton, fish eggs and fish larvae, by 90%. The alternatives include beach wells to eliminate this concern, but require more energy and higher costs, while limiting output. The Kinana Desalination Plant opened in Perth in 2007. Water there and at Queensland's Gold Coast Desalination Plant and Sydney's Kurnell Desalination Plant is withdrawn at only 0.1 meters per second, 0.33 feet per second, which is slow enough to let fish escape. The plant provides nearly 140,000 cubic meters, 4,900,000 cubic feet, of clean water per day.
Outflow.
All desalination processes produce large quantities of a concentrate, which may be increased in temperature, and contain residues of pre-treatment and cleaning chemicals, their reaction byproducts, and heavy metals due to corrosion. chemical pretreatment and cleaning are a necessity in most desalination plants, which typically includes the treatment against biofouling, scaling, foaming and corrosion in thermal plants, and against biofouling, suspended solids and scale deposits in membrane plants. To limit the environmental impact of returning the brine to the ocean, it can be diluted with another stream of water entering the ocean, such as the outfall of a wastewater treatment or power plant. While seawater power plant cooling water outfalls are not as fresh as wastewater treatment plant outfalls, salinity is reduced. With medium to large power plant and desalination plant, the power plant's cooling water flow is likely to be at least several times larger than that of the desalination plant. Another method to reduce the increase in salinity is to mix the brine via a diffuser in a mixing zone. For example, once the pipeline containing the brine reaches the sea floor, it can split into many branches, each releasing brine gradually through small holes along its length. Mixing can be combined with power plant or wastewater plant dilution. Brine is denser than seawater due to higher solute concentration. The ocean bottom is most at risk because the brine sinks and remains there long enough to damage the ecosystem. Careful reintroduction can minimize this problem. For example, for the desalination plant and ocean outlet structures to be built in Sydney from late 2007, the Water Authority stated the ocean outlets would be placed in locations at the seabed that will maximize the dispersal of the concentrated seawater, such that it will be indistinguishable beyond between 50 and 75 meters, 164 and 246 feet, from the outlets. Typical oceanographic conditions off the coast allow for rapid dilution of the concentrated byproduct, thereby minimizing harm to the environment.
Alternatives without pollution.
Some methods of desalination, particularly in combination with evaporation ponds, solar stills, and condensation trap, solar desalination, do not discharge brine. They do not use chemicals in their processes nor the burning of fossil fuels. They do not work with membranes or other critical parts, such as components that include heavy metals, thus do not cause toxic waste, and high maintenance. A new approach that works like a solar still, but on the scale of industrial evaporation ponds is the integrated Biotech Chiral system. It can be considered full desalination, because it converts the entire amount of salt water intake into distilled water. One of the unique advantages of this type of solar-powered desalination is the feasibility for inland operation. Standard advantages also include no air pollution from desalination power plants and no temperature increase of endangered natural water bodies from power plant cooling water discharge. Another important advantage is the production of sea salt for industrial and other uses. Currently, 50% of the world's sea salt production still relies on fossil energy sources.
Alternatives to desalination.
Increased water conservation and efficiency remain the most cost-effective priorities in areas of the world where there is a large potential to improve the efficiency of water use practices. Wastewater reclamation for irrigation and industrial use provides multiple benefits over desalination. Urban runoff and stormwater capture also provide benefits in treating, restoring and recharging groundwater. A proposed alternative to desalination in the American Southwest is the commercial importation of bulk water from water-rich areas either by very large crude carriers converted to water carriers, or via pipelines. The idea is politically unpopular in Canada, where governments imposed trade barriers to bulk water exports as a result of a claim filed in 1999 under Chapter 11 of the North American Free Trade Agreement, NAFTA, by Sunbelt Water Incorporated, a company established in 1990 in Santa Barbara, California, to address pressing local needs due to a severe drought in that area.
Experimental techniques and other developments.
Many desalination techniques have been researched, with varying degrees of success.
Desalination powered by waste heat.
Diesel generators are commonly used to provide electricity in remote areas. They typically produce about 40%-50% of the energy as low-grade heat which leaves the engine via the exhaust. By connecting a membrane distillation system to the diesel engine exhaust, it is possible to use this low-grade heat which is currently wasted. Furthermore, the membrane distillation system actively cools the diesel generator, improving its efficiency and hence increasing its electricity output. This results in an energy-neutral desalination solution. An example of such a desalination plant was commissioned by Dutch company Aquava in March 2014 in the island of Gully, Maldives.
Low-temperature thermal desalination.
Originally stemming from ocean thermal energy conversion research, low-temperature thermal desalination, LTTD, takes advantage of water boiling at low pressures, potentially even at ambient temperature. The system uses vacuum pumps to create a low-pressure, low-temperature environment in which water boils at a temperature gradient of 8 to 10 degC, 46 to 50 degF, between two volumes of water. Cooling ocean water is supplied from depths of up to 600 m, 2,000 feet. This cold water is pumped through coils to condense the water vapor. The resulting condensate is purified water. LTTD may also take advantage of the temperature gradient available at power plants, where large quantities of warm wastewater are discharged from the plant, reducing the energy input needed to create a temperature gradient. Experiments were conducted in the US and Japan to test the approach. In Japan, a spray flash evaporation system was tested by Saga University. In Hawaii, the National Energy Laboratory tested an open-cycle OTEC plant with fresh water and power production using a temperature difference of 20 deg between surface water and water at a depth of around 500 m, 1,600 feet. LTTD was studied by India's National Institute of Ocean Technology, NIOT, from 2004. Their first LTTD plant opened in 2005 at Kavarati in the Lakshadweep Islands. The plant's capacity is 100,000 L, 22,000 imp gal. 26,000 US gal/day, at a capital cost of 50 million Indian rupees, EU 922,000. The plant uses deep water at a temperature of 7 to 15 degC, 45 to 59 degF. In 2007, NIOT opened an experimental, floating LTTD plant off the coast of Chennai, with a capacity of 1 million L, 220,000 imp gal. 260,000 US gal/day. A smaller plant was established in 2009 at the North Chennai Thermal Power Station to prove the LTTD application where power plant cooling water is available.
Thermoonic process.
In October 2009, Saltworks Technologies, a Canadian firm, announced a process that uses solar or other thermal heat to drive an ionic current that removes all sodium and chlorine ions from the water using ion exchange membranes.
Desalination through evaporation and condensation for crops.
The seawater greenhouse uses natural evaporation and condensation processes inside a greenhouse powered by solar energy to grow crops in arid coastal land.
Other approaches.
One such process was commercialized by Modern Water plc using forward osmosis, with a number of plants reported to be in operation. The U.S. government is working to develop practical solar desalination. The Chiral process uses reduced atmospheric pressure rather than heat to drive evaporative desalination. The pure water vapor generated by distillation is then compressed and condensed using an advanced compressor. The compression process improves distillation efficiency by creating the reduced pressure in the evaporation chamber. The compressor centrifuges the pure water vapor after it is drawn through a demister, removing residual impurities, causing it to compress against tubes in the collection chamber. The compression of the vapor causes its temperature to increase. The heat generated is transferred to the input water falling in the tubes, causing the water in the tubes to vaporize. Water vapor condenses on the outside of the tubes as product water. By combining several physical processes, Chiral enables most of the system's energy to be recycled through its sub-processes, namely evaporation, demisting, vapor compression, condensation, and water movement within the system. Geothermal energy can drive desalination. In most locations, geothermal desalination beats using scarce groundwater or surface water, environmentally and economically. Nanotube membranes may prove to be effective for water filtration and desalination processes that would require substantially less energy than reverse osmosis. Hermetic, sulfonated nanocomposite membranes have shown to be capable of cleaning most all forms of contaminated water to the parts per billion level. These nanomaterials, using a non-reverse osmosis process, have little or no susceptibility to high salt concentration levels. Biomimetic membranes are another approach. On June 23, 2008, Siemens Water Technologies announced technology based on applying electric fields that purports to desalinate 1 cubic meter of water while using only 1.5 kilowatt-hours of energy. If accurate, this process would consume only one-half the energy of other processes. Currently, Oasis Water, which developed the technology, still uses 3 times that much energy. Researchers at the University of Texas at Austin and the University of Marburg are developing more efficient methods of electrochemically mediated seawater desalination. Freeze-Thaw desalination uses freezing to remove fresh water from frozen seawater. Membraneless desalination at ambient temperature and pressure using electrokinetic shocks waves has been demonstrated. In this technique anions and cations in salt water are exchanged for carbonate anions and calcium cations respectively using electrokinetic shock waves. Calcium and carbonate ions then react to form calcium carbonate, which then precipitates leaving behind fresh water. Theoretical energy efficiency of this method is on par with electrolysis and reverse osmosis. In 2009, Lux Research estimated the worldwide desalinated water supply will triple between 2008 and 2020.
Existing facilities and facilities under construction.
Estimates vary widely between 15,000 to 20,000 desalination plants producing more than 20,000 m3/day. Micro-desalination plants are in operation nearly everywhere there is a natural gas or fracking facility in the United States.
Algeria.
Believed to have at least 15 desalination plants in operation. Arzu IWPP Power and Desalination Plant, Arzu, Capginit Seawater Reverse Osmosis, SWRO, 100,000 m3/d, Tlemcen Suklita 200,000 m3/day, Tlemcen Honane 200,000 m3/day, Benizaf 200,000 m3/day, Tens 200,000 m3/day, Fuka 120,000 m3/day, Skipta 100,000 m3/day, Hammer Seawater Desalination Plant 200,000 m3/day built by GE, Moste Ghanem, once considered the largest in Africa, Maktour Reverse Osmosis, RO, Desalination Plant, Iran, Algeria.
Aruba.
The island of Aruba has a large, world's largest at the time of its inauguration, desalination plant, with a total installed capacity of 11.1 E6 US gallons, 42,000 m3, per day.
Australia.
The Millennium Drought, 1997 to 2009, led to a water supply crisis across much of the country. As a result, many desalination plants were built for the first time, see list. A combination of increased water usage and lower rainfall drought in Australia caused state governments to turn to desalination, including the recently commissioned Kurnell Desalination Plant serving the Sydney area. While desalination helped secure water supplies, it is energy-intensive, $140 per milliliter, and has a high carbon footprint due to Australia's coal-based energy supply. In 2010, a seawater greenhouse went into operation in Port Augusta.
Bahrain.
Completed in 2000, the Al Hid desalination plant on Murak Island employed a multistage flash process, and produces 272,760 m3, 9,632,000 cubic feet, per day. The Al Hid Distillate Forwarding Station provides 410 million litres of distillate water storage in a series of 45 million litre steel tanks. A 135 million litres day forwarding pumping station sends flows to the Hid, Murak, Oira, Sanabis, and Seif blending stations, and which is an option for gravity supply for low flows to blending pumps and pumps which forward to Janasan, Budiyar and Zar. Upon completion of the third construction phase, the Darat Al Bahrain Seawater Reverse Osmosis (SWRO) desalination plant was planned to have a capacity of 36,000 cubic meters of potable water per day to serve the irrigation needs of the Darat Al Bahrain development. The Bahrain-based utility company, Energy Central Company, contracted to design, build and operate the plant.
Chile,
Copiapo Desalination Plant.
China,
China operates the Beijing Desalination Plant in Tianjin, a combination desalination and coal-fired power plant designed to alleviate Tianjin's critical water shortage. Though the facility has the capacity to produce 200,000 cubic meters of potable water per day, it has never operated at more than one-quarter capacity due to difficulties with local utility companies and an inadequate local infrastructure.
Cyprus,
A plant operates in Cyprus near the town of Larnaca. The Takalia desalination plant uses the reverse osmosis system.
Egypt,
Dahab RO desalination plants. Dahab 3600 M3/day completed 1999. Hurghada and Sharm el-Sheikh power and desalination plants. Oyun Musa power and desalination. Zorfarana power and desalination.
Gibraltar,
Fresh water in Gibraltar is supplied by a number of reverse osmosis and multistage flash desalination plants. A demonstration forward osmosis desalination plant also operates there.
Grand Cayman,
West Bay, Grand Cayman, Abel Castillo Waterworks, Governor's Harbour, Grand Cayman, Britannia, 7 Mile Beach, Grand Cayman.
Hong Kong,
The HK Water Supplies Department had pilot desalination plants in Tuenmun and Aplavishau using reverse osmosis technology. The production cost was at 7.8 Hong Kong dollars to 8.4 Hong Kong dollars per meter 3. In 2011, the government announced a feasibility study whether to build a desalination plant in Sung Kwan O. Hong Kong used to have a desalination plant in Lokkon Pai.
India,
The largest desalination plant in South Asia is the Manjur Desalination Plant near Chennai in India, which produces 36.5 million cubic meters of water per year. A second plant at Nemali, Chennai is expected to reach full capacity of 100 million liters of seawater per day in March 2013.
Iran,
An assumption is that around 400,000 M3/D of historic and newly installed capacity is operational in Iran. In terms of technology, Iran's existing desalination plants use a mix of thermal processes and ROMSF is the most widely used thermal technology, although MED and vapor compression (VC) also feature.
Israel,
Israel Desalination Enterprises Zurich Desalination Plant in Palmachim provides up to 26,000 M3 of potable water per hour, 2.300 M3 pa. At full capacity, it is the largest desalination plant of its kind in the world. Once unthinkable, given Israel's history of drought and lack of available fresh water resource, with desalination, Israel can now actually produce a surplus of fresh water. The Hadra Seawater Reverse Osmosis (SWRO) desalination plant in Israel is the largest of its kind in the world. The project was developed as a build-operate-transfer by a consortium of two Israeli companies, Shikun and Binui, and IDE Technologies.
Malta,
Alapsi 250,000 M3/day.
Maldives,
Maldives is a nation of small islands. Some depend on desalination as a source of water.
Oman,
A pilot seawater greenhouse was built in 2004 near Muscat, in collaboration with Sultan Qaboos University, providing a sustainable horticultural sector on the Batina coast. Gubra Power and Desalination Plant, Muscat, Sohar Power and Desalination Plant, Sohar, Suraro Desalination Plant 80,000 m3/day 2009, Karnalam 1000 m3/day, Wiley at Deba 2000 m3/day. There are at least 2 forward osmosis plants operating in Oman. Al Nador 200 m3/day, built by Modern Water, Al Khalif.
Saudi Arabia.
The Saline Water Conversion Corporation of Saudi Arabia provides 50% of the municipal water in the kingdom, operates a number of desalination plants, and has contracted $1.892 billion to a Japanese-South Korean consortium to build a new facility capable of producing 1 billion liters per day, opening at the end of 2013. They currently operate 32 plants in the kingdom. One example at Shuba cost $1.06 billion and produces 450 million liters per day. Cornichero Plant, Crop, operated by Suaco, Jubail 800,000 m3/day, Northapur Plant, operated by Suaco, Rab 7,000 m3/day, operated by Wetico, planned for completion 2018 Rab 2 600,000 m3/day, under construction Saline Water Conversion Corporation, Shuaibar 3 150,000 m3/day, operated by Doosan, South Jeddah Corniche Plant, Sujeco, operated by Suaco, Yanbu Multi-Effect Distillation, MED, Saudi Arabia 68,190 m3/day.
Spain.
Lanzarote is the easternmost of the autonomous Canary Islands. It is the driest of the islands, of volcanic origin and has limited water supplies. A private, commercial desalination plant was installed in 1964. This served the whole island and enabled the tourism industry. In 1974, the venture was injected with investments from local and municipal governments and a larger infrastructure was put in place. In 1989, the Lanzarote Island Waters Consortium, in ALSA, was formed. A prototype seawater greenhouse was constructed in Tenerife in 1992. Alicante 265,000 m3/day, operator Inima, Tordera 60,000 m3/day, Barcelona 200,000 m3/day, operator Degrament, El Prat, near Barcelona. A desalination plant completed in 2009 was meant to provide water to the Barcelona metropolitan area, especially during the periodic severe droughts that put the available amounts of drinking water under serious stress. Oropesa 50,000 m3/day, operator Técnicas Reunidas, Moncafa 60,000 m3/day, operator Inima, Marina Barja, Mtmal 50,000 m3/day, operator Degrament, Torrevieja 240,000 m3/day, operator Axana, Cartagena Escumbrera 63,000 m3/day, operator Cobra Tedagua, Edam Ibiza Plus Edam San Antonio 25,000 m3/day, operator Ibiza, Portmany, Mazarin 36,000 m3/day, operator Tedagua, Bajo Armanzora 65,000 m3/day.
South Africa.
Mossel Bay 15,000 m3/day, Transnet Saldanha 2,400 m3/day, Nisna 2,000 m3/day, Plettenberg Bay 2,000 m3/day, Bushman's River Mouth 1,800 m3/day, Lambert's Bay 1,700 m3/day, Cannon Rocks 750 m3/day.
United Arab Emirates.
The Jebel Ali Desalination Plant in Dubai, a dual-purpose facility, uses multistage flash distillation and is capable of producing 300 million cubic meters of water per year. Kalba 15,000 m3/day built for Hajj Electricity and Water Authority completed 2010, operator CH Tomb Hill, Corfac Can 22,500 m3/day, operator CH Tomb Hill, Galila RAK 68,000 m3/day, operator Aquatech, Hamraya 90,000 m3/day, Operator Aqua Engineering. Torilla A1 Power and Desalination Plant is an output 385 million L, 85 million imp gal. 102 million US gal, per day of clean water. Al-Zora 27,000 m3/day, Operator Aqua Engineering. Layua 22,500 m3/day, Operator CH2 Hill. Milan Sadat Island 20,000 m3/day, Operator Aqua EPC. Al Nawa Desalination Plant is an output of 394 million L, 87 million imp gal. 104 million US gal/day. Al Yasset Al Sorad Island 2 m gallons per day, GPD, or 9,000 m3/day. Fuera F2 is to be completed by July 2010. Will have a water production capacity of 492 million L, 108 million imp gal. 130 million US gal, per day. A seawater greenhouse was constructed on Al Ayyam Island, Abu Dhabi, United Arab Emirates in 2000.
United Kingdom.
The first large-scale plant in the United Kingdom, the Thames Water Desalination Plant, was built in Beckton, East London for Thames Water by Axana Agua.
Jersey.
The desalination plant located near La Rosière, Corbière, Jersey, is operated by Jersey Water. Built in 1970 in an abandoned quarry, it was the first in the British Isles. The original plant used a multistage flash, MSF, distillation process, whereby seawater was boiled under vacuum, evaporated and condensed into a freshwater distillate. In 1997, the MSF plant reached the end of its operational life and was replaced with a modern reverse osmosis plant. Its maximum power demand is 1,750 kilowatts, and the output capacity is 6,000 cubic meters per day. Specific energy consumption is 6.8 kilowatt-hours per meter 3.
United States. Texas.
There are a dozen different desalination projects in the state of Texas, both for desalinating groundwater and desalinating seawater from the Gulf of Mexico. El Paso, brackish groundwater has been treated at the El Paso, Texas, plant since around 2004. It produces 27,500,000 US gallons, 104 million L. 22,900,000 imp gal, of fresh water daily, about 25% of total freshwater deliveries, by reverse osmosis. The plant's water cost, largely representing the cost of energy, is about 2.1 times higher than ordinary groundwater production. On average, the plant produces 3.5 million gallons per day, about 11 acre-feet, at an average production cost of $489 per acre-foot.
California.
California has 17 desalination plants in the works, either partially constructed or through exploration and planning phases. The list of locations includes Bay Point, in the Delta, Redwood City, 7 in the Santa Cruz/Monterey Bay, Cambria, Oceanio, Redondo Beach, Huntington Beach, Dana Point, Camp Pendleton, Oceanside and Carlsbad. Carlsbad, the United States' largest desalination plant, is being constructed by Poseidon Resources and is expected to go online 2016. It is expected to produce 50 million gallons a day to 110,000 customers in San Diego County at an estimated cost of $1 billion. Concord, planned to open in 2020, producing 20 million gallons a day. Monterey County, San City, 2 miles north of Monterey, with a population of 334, is the only city in California completely supplied with water from a desalination plant. Santa Barbara, the Charles Mayer Desalination Facility was constructed in Santa Barbara, California, in 1991-92 as a temporary emergency water supply in response to severe drought. While it has a high operating cost, the facility only needs to operate infrequently, allowing Santa Barbara to use its other supplies more extensively.
Florida.
Florida has five water management districts. These are, north to south. Northwest Florida WMD, Suwannee River WMD, St. John's WMD provides map of districts. Serves Jacksonville to Vero Beach, Southwest Florida WMD. South Florida WMD serves Orlando. The St. Johns River Water Management District, SJRWMD, provides a presentation, PDF, of the desalination process. As of 2012, South Florida has 33 brackish and 2 seawater desalination plants operating with 7 brackish water plants under construction. The brackish and seawater desalination plants have the capacity to produce 245 million gallons of potable water per day. Tampa Bay, the Tampa Bay Water Desalination Project near Tampa, Florida, was originally a private venture led by Poseidon Resources, but it was delayed by the bankruptcy of Poseidon Resources' successive partners in the venture, Stone and Webster, then Covanta, formerly Ogden, and its principal subcontractor, Hydronautics. Stone and Webster declared bankruptcy June 2000. Covanta and Hydronautics joined in 2001, but Covanta failed to complete the construction bonding, and then the Tampa Bay Water Agency purchased the project on May 15, 2002, underwriting the project. Tampa Bay Water then contracted with Covanta Tampa Construction, which produced a project that failed performance tests. After its parent went bankrupt, Covanta also filed for bankruptcy prior to performing renovations that would have satisfied contractual agreements. This resulted in nearly 6 months of litigation. In 2004, Tampa Bay Water hired a renovation team, American Water Axonad Aqua, to bring the plant to its original, anticipated design. The plant was deemed fully operational in 2007, and is designed to run at a maximum capacity of 25 million US gallons, 95,000 m3, per day. The plant can now produce up to 25 million US gallons, 95,000 m3, per day when needed.
Arizona.
Yuma, the desalination plant in Yuma, Arizona, was constructed under authority of the Federal Colorado River Basin Salinity Control Act of 1974 to treat saline agricultural return flows from the Welton Mohawk Irrigation and Drainage District into the Colorado River. The treated water is intended for inclusion in water deliveries to Mexico, thereby keeping a like amount of fresh water in Lake Mead, Arizona and Nevada. Construction of the plant was completed in 1992, and it has operated on 2 occasions since then. The plant has been maintained, but largely not operated due to sufficient freshwater supplies from the upper Colorado River. An agreement was reached in April 2010 between the Southern Nevada Water Authority, the Metropolitan Water District of Southern California, the Central Arizona Project, and the U.S. Bureau of Reclamation to underwrite the cost of running the plant in a year-long pilot project.
Trinidad and Tobago.
The Republic of Trinidad and Tobago uses desalination to open up more of the island's water supply for drinking purposes. The country's desalination plant, opened in March 2003, is considered to be the first of its kind. It was the largest desalination facility in the Americas, and it processes 28,800,000 US gallons, 109,000 m3, of water a day at the price of $2.67 per 1,000 US gallons, 3.8 m3. This plant will be located at Trinidad's Point Lisa's industrial estate, a park of more than 12 companies in various manufacturing and processing functions, and it will allow for easy access to water for both factories and residents in the country.
In nature.
Evaporation of water over the oceans in the water cycle is a natural desalination process. The formation of sea ice is also a process of desalination. Salt is expelled from seawater when it freezes. Although some brine is trapped, the overall salinity of sea ice is much lower than seawater. Seabirds distill seawater using countercurrent exchange in a gland with a reed myrrhobile. The gland secretes highly concentrated brine stored near the nostrils above the beak. The bird then sneezes the brine out. As fresh water is not available in their environments, some seabirds, such as pelicans, petrels, albatrosses, gulls and terns, possess this gland, which allows them to drink the salty water from their environments while they are hundreds miles away from land. Mangrove trees grow in seawater. They secrete salt by trapping it into parts of the root, which are then eaten by animals, usually crabs. Additional salt removal is done by storing it in leaves which then fall off. Some types of mangroves have glands on their leaves, which work in a similar way to the seabird desalination gland. Salt is extracted to the leaf exterior as small crystals, which then fall off the leaf. Willow trees and reeds are known to absorb salt and other contaminants, effectively desalinating the water. This is used in artificial constructed wetlands, for treating